Hi, my name is Andreas Reisinger and today we are visiting the BM Lab, which is the Biomechanics lab at the Karl Landsteiner University in Krems, and we will check out a project where we attempt to print femoral human bone out of plastics on a 3D printer to have test specimens for example, orthopedic studies. So let's have a look. Hi Kathi.
Hi Andreas.
This is Katharina Negel. She is a PhD student in our group in Krems, and she is working currently on a project where she uses 3D printing to produce artificial human femoral bones, such as this one. So why are we doing this? When you do mechanical testing, and it's not so important that you really precisely reproduce the mechanical properties of the bone, which can be
implant testing,
testing of nails, of plates and screws. This can be done on artificial bones too. And what I have here is a commercial artificial bone. And advantages and disadvantages of this, but why are you with 3D printing bones, Kathi, when you can actually buy artificial bones already?
So as you might see, this bone is just a simplification of a human femur, and you're limited to this geometry of the manufacturer. And if you want to do more tests due to like studies or series of studies for the implantation of an implant, stuff like that, so you need more bones, and this would be quite expensive depending on the quality you wish to have. And for the 3D printed bone, as you can see here, this for example has the geometry of an actual patient, so you can vary the geometry quite easily when you have the CT scan of a patient or of the artificial bones. And you can also overnight print your bones, so you're not limited to the supply of the manufacturer.
Okay, so let's have a look what Kathi is doing. Kat. Okay, Kathi, we are now in your office to answer the question, how does the 3D printer know what to print? So when you print a human femoral bone, how do you get the data?
So first I had to perform imaging. So it was necessary to do a micro CT of the artificial bones, and the result of this scan you can see here. But as you also can see in this picture, you also see the embedding and the structure holder. So in the first step, it was necessary to get rid of this holder and embedding, and this was done step by step with applying different filters in MATTool. And as you can see here, you then get kind of the cortex of the bone, and with doing fine-tuning of the segmentation, you end up with the cortex, as you can see in this picture. And with that, I already had the cortex, but how about the spongiosa? So it was necessary to fill the whole bone again, and then subtract these two pictures from each other to end up with the spongiosa. So in the end, we had two STL files, one for the cortex and one for the spongiosa, and then it was also necessary to choose, okay, which infill do we use for the spongiosa.
Okay, so you are printing two different STLs actually. So this is the inner part.
Yes.
And
this is the outer
part. So these two images are printed.
Yes.
At the same time in one model.
Yes.
Okay, let's have a look. Okay, this is now the slicer program where we can see the actual model that is to be printed. Can we have a look inside, Kathi?
Of course.
To see the two different kinds of materials or densities.
As you can see here, the cortex is varying throughout the whole bone sample. And here you can nicely see also the spongiosa.
Okay, so this is the infill region.
Yes, and for the cortex, as it is compact, should be compact, we used 100% infill density. And for the spongiosa, we actually matched with a power law the infill density to the actual bone density or the density of the foam of the artificial bones.
Okay, what do we see here?
So as you can see here, it started to print the supporting structure and already started in the end here to start print the bone. And as you can see here, the whole print will take approximately 12 hours and it's only printed 2% of our model.
That's not much, so we have to wait till tomorrow.
3 days later.
Right.
2,000 years later.
So in the next step we have to embed this printed bone. For this we use this embedding form. So you can see, like as I explained, this plate is to help to place them in the right position. For that reason this is placed here. I marked positions here. Then gently then when we put that, we go to the embedding zone. Put away a sample. So we will embed this in polyurethane form. For that reason we need two different solutions. First the polyurethane itself and then the isocyanate for the cross-linking of the material so it gets hard.
The rule of thumb is, if you think that you can stop steering, steer more.
And now we have to wait
How long?
about 20 to 30 minutes.
Yeah, then it should be cured. So why do you need the alignment ring there? Because you just put the sample to the bottom of the mold.
Yes.
As before. And why do you need the ring again?
To make really sure that the position is fixed while I'm pouring in the solution.
So that it does not wiggle.
Yes.
Okay, did the resin cure? Is it hard?
I think so, yes.
Perfect.
So then we can take this to the working bench.
So you see, it's really important to put some trench spray, it's a separation spray in the mold.
Don't forget.
Are we finished now?
No. We still need an embedding for the head.
Therefore, Kati has a special device that allows to mount the sample at a certain angle and to dip it into a soup of embedding.
So for the embedding of the head we have like this half sphere thank you, and this block to make sure that it's not wiggling around, so it stays in place, actually to stay in place for every sample. So again we need the separation spray.
Look at this beauty. Okay, we are continuing now with the mechanical testing. For this we have our Zwick 030 here, which can apply quasi-static loading up to 30 kilonewtons in this load frame. And we are mounting the sample in there, compress it till fracture, and measure fracture load and displacement till fracture. But how are we doing this? We are not applying the load in any random direction. No, we would like to reproduce the standing load case. What does this mean? When I stand here on the floor, my femoral bones are loaded in a certain direction because of my body weight, and this is reproduced here in this test setup. That means I'm not mounting the sample in any random way. No, I have to incline it in a certain angle in this direction, also in this rotating direction, to really reproduce what is happening in the human body. And then we apply a simulated body weight and increase it a lot further until the bone fractures in this standing load case. So what is happening is this crosshead is moving up and down. We're measuring force here in the 6-axis load cell and displacement in the load frame.
So for this, we place the bone in the holder, have to fix everything.
Wait a second. Yeah. Why do you have such an embedding cup here at the top of the bone on the head?
So we want to make sure that the bone is breaking at the neck, or we wish the bone to break in the neck and not directly on the head, because due to the printing, as you can maybe see, fine layers, layer by layer. It is printed layer by layer, and then if we apply it directly on the head, it could be that our results would be influenced by layer splitting.
Aha, so that means that the head would split instead of the neck.
Yes.
This is what we don't want. So,
and as you can see now, it is leveled. Now we still have to.
So it's centered.
Centered.
Okay. There's still a gap of around 4 millimeters. So now is the correct time to zero all the sensors. Currently we have a small gap between the plate and the sample, and now we should zero the values for the load cell. So you see all the force directions, Fx, Fy, Fc, and the moments, and we zero them. Okay, and then we can go back to the load frame software, and we see now that the load is approximately 0, and from this value we can go on.
Ready, set, go.
Have a look, this is the force displacement curve. So we already went over the peak, maximum load of 4,000 newtons. So this is the fractured sample, and you see that it was not breaking at the neck precisely, but the head was crushed onto the neck itself. Good. Wow, that was intense. Kati, so what can we say about this sample from the force time plot?
In the force time. As you can see here, you first have this time frame where nothing is happening. Then you have here the contact point where the sample gets in contact with the force plate. Then you have a linear, almost linear increase. So this is, you can say, the linear elastic region of our sample. Then with this slightly,
slight bump here.
Bump here indicates a first fracture. Then it's like deforming plastically until it ruptures at this point. So in total, you can see our sample took around like 60 or 80 seconds to be fractured.
And we had a maximum load of
Around 4,200 newtons.
Wahnsinn. Nice one. Okay, here you see two tested specimens with actually quite realistic modes of failure. In both cases the neck fractured. In this case the head was thrown away. In this case the head was crushed onto the neck. But both of these two modes are quite realistic, because when you do testing on real donor bones you find the same modes of failure.